Chapter 6, Definite Integrals.
Section A, Fundamental Theorem of Calculus. Definition of a definite integral. If f is continuous on the closed interval a to b and big F prime is equal to f, then according to the fundamental theorem of calculus, the integral of f of x from a to b equals big FB minus big FA. Here, the integral of f of x from a to b is the definite integral of f from a to b. F of x is called the integrand, and a and b are called, respectively, the lower and upper limits of integration. This important theorem says that if f is the derivative of big F, then the definite integral of f gives the net change in big F as x varies from a to b. It also says that we can evaluate any definite integral for which we can find an antiderivative of continuous function.
For this example, we have a simple integration problem. X cubed from 0 to 2. First, we integrate using power rule and get x to the fourth over 4 from 0 to 2. We now have to use the fundamental theorem of calculus to get f of b minus f of a. This will give us 16 over 4 minus 0, which is equal to 4.
Properties of definite integrals. These theorems about definite integrals are important. The first theorem states that a derivative of an integral of a function is always equal to that function. The second theorem states that a constant times a function within an integral can always be pulled out in front of the integral. The third theorem states that any integral with equal limits of integration is always equal to 0. The fourth theorem states that the limits of integration of an integral can be swapped by just making the integral negative. The last theorem states that an integral from a to c plus an integral from c to b is equal to an integral from a to b. If f and g are both integrable functions of x on a to b, then the integral of f of x plus or minus g of x equals the integral of f of x plus or minus the integral of g of x. The mean value theorem for integrals. If f is continuous on a to b, there exists at least one number, c, that is greater than a and less than b, such that the integral of f of x dx from a to b is equal to f of c times b minus a. By the comparison property, if f and g are integrable on a to b, and if f of x is less than or equal to g of x for all x in a to b, then the integral of f of x dx from a to b is less than or equal to the integral of g of x dx from a to b. For this example, we'll be using the theorem of functions added or subtracted within integrals. Here we can split up the integral into two separate integrals. Note in this step you can also pull out the constants. Now all that is left to do is integrate. After integrating and solving, we come to the solution of 48.
Integrals involving parametrically defined functions.
This example uses a curve given parametrically by x equals 1 minus cosine t and y equals t minus sine t, where 0 is less than or equal to t and t is less than or equal to pi. we're trying to find an equivalent integral to the given integral y dx from 0 to 3 halves. First, we have to find dx because it is given in the given integral. This comes out to be sine t dt. Now we can plug y into our integral and substitute dx for dx. Now we're going to have to find our limits of integration. For this, we can set the first limit of integration 0 into our x equation and use it as x. So we're trying to find a value t for which x equals 0. In this case, 1 equals cosine t. Cosine is equal to 1 at 0. So our first limit of integration is 0. Next, we have to find our upper limit of integration. So we can use 3 halves from the given problem as our x value, and we have to find a given t value for that function. This gives us negative 1/2 equals cosine of t. Cosine of t equals negative 1/2. This gives us t equals 2 pi over 3, using all students take calculus. So now that we have our upper and lower limits, we can have our final solution to the problem.
Section D. Definition of definite integral as the limit of a sum. The fundamental theorem again. Most applications of integration are based on the fundamental theorem of calculus. This theorem provides the tool for evaluating an infinite sum by means of definite integral. Suppose that a function f of x is continuous on the closed interval a to b. Divide the interval into n subintervals of lengths delta x sub k. Choose numbers, one in each subinterval, as follows: x sub 1 in the first, x sub 2 in the second, and so on and so forth for x sub k in the kth, and x sub n in the nth. The limit of the sum of f of x sub k times delta x sub k as n approaches infinity equals the integral of from a to b of f of x equals big F of b minus big F of a, where the derivative of big F of x equals f of x. So the sum of f of x sub k times delta x is called a Riemann sum. For finding the area under the curve, if f of x is non-negative on a to b, we see that f of x sub k times delta x sub k can be regarded as the area of a typical approximating rectangle. As the number of rectangles increases, or, equivalently, as the width delta x of the rectangles approaches 0, the rectangles become an increasingly better fit to the curve. The sum of their areas gets closer and closer to the exact area under the curve. Finally, the area bounded by the x-axis, the curve, and the vertical lines x equals a and x equals b is given exactly by the limit of the sum of f of x sub k times delta x as n approaches infinity. If the graph is negative, then any area above the graph and below the x-axis is counted as negative. The shaded area above the curve and below the x-axis equals the negative integral of f of x from a to b. where the integral yields a negative number. Note that every product f of x sub k times delta x in the shaded region is negative, since f of x sub k is negative for all x between a and b. We see from the graph that the graph of f crosses the x-axis at c. That area, a sub 1, lies above the x-axis, and the area a sub 2 lies below the x-axis. This is shown by the formula integral of f of x from a to b equals the integral of f of x from a to c plus the integral of f of x from b to c. Therefore, the integral of f of x from a to b equals a sub 1 minus a sub 2. If f is continuous, then the area between the graph of f on a to b and the x-axis is given by the integral of absolute value of f of x from a to b. This implies that over any interval within a to b for which f of x is less than 0, the absolute value of f of x equals negative f of x. This can be shown by the integral of the absolute value of f of x from a to b equals the integral of f of x from a to c minus the integral of f of x from c to b.
Approximations to the definite integral Riemann sums. It is always possible to approximate the value of a definite integral even when an integrand cannot be expressed in terms of elementary functions. If f is non-negative on a to b, we interpret the integral f of x dx from a to b as the area bounded above by y equals f of x, below by the x-axis, and vertically by the lines x equals a and x equals b. The value of the definite integral is then approximated by dividing the area into n strips, approximating the area of each strip by a rectangle or other geometric figure, then summing these approximations. In this section, we will divide the interval from a to b into n strips of equal width delta x. Using rectangles, we may approximate the integral of f of x dx from a to b by any of the following sums: left sum, right sum, or midpoint sum. For this example, we'll be finding a left sum. Approximate the function x cubed on the interval 0 to 2 by using 4 subintervals. We use delta x, which is the width of each rectangle. We find delta x by setting b minus a over the number of subintervals, or n, which equals 4. This comes out to be 1/2. Now we use 1/2 and plug that into our formula. After solving the equation, we get 36 over 16, which comes out to be 9/4. A more accurate approximation can be made using trapezoids. We now find the area of the strips in the graph by using trapezoids. We denote the bases of the trapezoids by y sub 0, y sub 1, and y sub n, and the heights by delta x equals h. The first sum approximates the area between f and the x-axis from a to b. The second sum is the result of removing the common factor h over 2. The last sum uses t of n to denote the approximating sum with n subintervals. This is the trapezoid rule. For this example, we will use the trapezoid rule to approximate the same function, x cubed. We see here that delta x is equal to h, and we know from the previous example that delta x is equal to 1/2, therefore h is equal to 1/2. Now we plug this into our equation. After solving the equation, we come to the solution of 17/4.
Interpreting natural log of x as an area. It is common to define natural log of x as a definite integral, as natural log of x equals the integral from x to 1 of 1 over t dt when x is greater than 0. This integral can be interpreted as the area bounded above by the curve y equals 1 over t when t is greater than 0. On the next slide by the t-axis, at the left by t equals 1, and at the right by t equals x when x is greater than 1. Note that if x equals 1, the above definition yields natural log 1 equals 0, and if 0 is less than x is less than 1, we can rewrite as follows. Natural log of x equals the negative integral from x to 1 of 1 over t times dt, showing that natural log is less than 0 if 0 is less than x is less than 1. With this definition of natural log of x, we can approximate natural log of x using rectangles or trapezoids.
If the function y equals f of x is continuous on the interval a is less than or equal to x is less than or equal to b, then we can define the average value of f from a to be 1 over b minus a times the integral of f of x from a to b. Note that this is equivalent to the average value of f times b minus a equals the integral of f of x from a to b.
To find the average value of the function, we take the integral of that function and multiply it by 1 over b minus a. This example uses the function 9x squared on the interval 1 to 4. We set up the integral using 9x squared from 1 to 4 and multiply it by 1 over 4 minus 1. This is 1/3. We have now integrated and reached the conclusion of x cubed on the interval 1 to 4. We now use the fundamental theorem of calculus to say 4 cubed minus 1 cubed. This comes out to be 64 minus 1, which leaves us with our solution 63.